In our lesson today, we're going to learn about useful exponent properties that will allow us to simplify expressions that contain exponents. Before we get into some good examples, let's do a quick review of what we've learned about exponents earlier in the year. Remember that exponents represent repeated multiplication. If I have 3 raised to the fourth power, then that's the same as 3 times 3 times 3 times 3. And if you evaluate that product, you would end up with 81. This is the exponential form, this is the expanded form, and this is the evaluated form. When written in exponential notation, 3 to the fourth power, the 3 right here is called the base, and the 4 is, of course, the exponent. Any number that we raise to the first power is equal to itself. 8 to the first power equals 8. Any number raised to the 0 power will be equal to 1. 5 to the 0 power equals 1. 12 to the 0 power equals 1. If you have a number raised to the power of 0, then it will always be equal to 1. There are other special properties that relate to exponents that we will investigate now. One of the simplest is shown below, where we'll be multiplying numbers with the same base. Consider this expression 2 to the third power times 2 to the second power, or 2 cubed times 2 squared. How can we rewrite this as 2 with a single exponent? Okay, well, let's rewrite each part of the expression in expanded form. 2 to the third power means to do 2 times 2 times 2. And 2 squared means to do 2 times 2. Now that we understand what both of those mean, let's rewrite the entire expression as 2 raised to a single power. So 2 to the third times 2 squared is equal to 2 times 2 times 2, that's 2 to the third power, times 2 squared, which is 2 times 2. Notice that the base is the same here. We had a 2 as the base every time, so I'm going to use 2 as my base again. And now I have 5 copies of the number 2 that I'm multiplying together. This is equal to 2 to the fifth power. So 2 to the third power times 2 to the second power is equal to 2 to the fifth power. Hopefully you noticed here that all I needed to do, because the bases were the same, was add those exponents together. 3 plus 2 is equal to 5. And that's exactly what we have here in property number 1. Okay, this tells us that when you multiply two expressions with the same base, we keep that base and we add the exponents. All right, both of these had a base of 2, so I kept that base, and then 3 plus 2 gave me 5. Keep the base, add the exponents together. X to the a times x to the b is equal to x to the a plus b power. Does this work if the bases are different? Okay, so if I had, for example, 2 to the third power times 4 to the, let's go with the second power. Okay, is that equal to 8, because 2 times 4 is 8, to the fifth power? All right, well, 2 to the third power, that's 2 times 2 times 2, which is equal to 8, times 4 to the second power, well, that's 16. And if you were to multiply 8 by 16, you would get 128. All right. Is that equal to 8 to the fifth power? Well, let's check it out on our calculator. 8, I'm going to raise it to the fifth power. And notice I get 32,768. Well, very clearly, these two numbers are not equal to each other. So no, okay? This does not work if the bases are different. So again, when you multiply two expressions with the same base, keep that base and add the exponents. Let's go ahead and do some practice where we're multiplying with the same base. All right, in the top 3 examples, it says to rewrite each product using a single base and an exponent. So I have y to the 7th power times y to the 4th power. The bases are the same, so I'm going to keep the base, and I'm going to add the exponents together. 7 plus 4 equals 11. So this would become y to the 11th power. Next, I have 1/2 raised to the 3rd power times 1/2. Remember that when a number is by itself like this, it really has an exponent of 1. So we can think about that as 1/2 to the first power. So again, I'm going to keep my base. They're both 1/2. And now I'm going to raise that to the 3 plus 1, or the fourth power. That's 1/2 to the fourth power. If I wanted to, I could go ahead and evaluate this. Okay, that's going to be the same as 1 to the fourth power. Well, 1 times 1 times 1 times 1 is 1. And 2 to the fourth power. 2 times 2 is 4, times 2 is 8, times 2 is 16. So this would be equal to 1/16 if I evaluated it. Next, I have x to the third, y to the fourth, times x to the fifth, y squared. Notice that here the bases aren't the same, so I can't do anything with these. And same thing over here, these bases aren't the same. But remember, this is multiplication, and multiplication is commutative. So I could rewrite this as x cubed times x to the fifth times y to the fourth times y squared. And then I can I can multiply the x's together. X to the third times x to the fifth is x to the eighth power. And I can do the same thing with the y's. Y to the fourth times y squared is y to the sixth power. So my simplified expression now says x to the eighth y to the sixth power. Underneath, we're going to rewrite each product by multiplying the constants and the variables. So just like we did up here, remember that multiplication is commutative. 5m squared times 7m to the fifth. I can rearrange this so that my constants are together, 5 times 7, times my variables of m squared times m to the fifth. Well, 7 times 5, I know that's going to give me 35. And m squared times m to the fifth, it's the same base m. 2 plus 5 is 7. Negative 3x squared times x to the sixth. Again, I can get my constants together, negative 3 times 6, times x squared times x. Negative 3 times 6 is negative 18. X squared times x, again, that's x to the first power. That's going to be x to the third. So we get negative 18 x to the third power. 1/2 y cubed times 4/5 y squared. I'll get my fractions together, 1/2 times 4/5 times the y's, y cubed times y squared. I have fractions here that I'm going to multiply. Before I multiply, though, I'm going to simplify the 2 and the 4. 2 goes into itself once and into 4 twice. No other simplifying can be done. 1 times 2 is 2. 1 times 5 is 5, so we get 2/5. And then y to the third times y to the second is y to the fifth power. So we have 2/5 y to the fifth. And finally, we have 2ab squared times 8a cubed b squared. So we have our constants, 2 times 8, times the a's, a times a to the third, times the b's, b squared times another b squared. All right, well, 2 times 8 makes 16. A, which is a to the first, times a to the third is a to the fourth power. And b squared times b squared, well, that's b to the fourth power. 16, a to the fourth, b to the fourth. The next exponent property that we're going to investigate is when we raise a power to another power. Consider the expression 2 squared cubed. 2 to the second power, that whole thing raised to the third power. How would you write this as 2 with a single exponent? Well, again, first thing we're going to do is rewrite this expression in expanded form. When you cube something, that means you're going to multiply it by itself 3 times. I'm cubing 2 to the second power. So I'm going to do 2 to the second power times 2 to the second power times 2 to the second power. I have 3 copies of 2 to the second that I'm multiplying by each other. Now I'm going to rewrite this expression with a single exponent. I can apply the first property that I had, where if the bases are the same and I'm multiplying, I keep that base, and all I have to do is add the exponents together. 2 plus 2 plus 2 is equal to 6. So the expression that we had, 2 to the second power raised to the third power, is equal to 2 to the sixth power. What do you notice? Well, hopefully you saw here that what you had to do was keep the base, and to get the exponent of 6, all you had to do was multiply the exponents together. Okay, so let's write that down. You need to multiply the exponents. All right, when you're raising a power to a power, you just need to multiply the exponents. So that's what we have down here in property number 2. To raise a power to a power, again, keep the base, and then you multiply the exponents together. X to the a power, all raised to the b power, is equal to x to the a times b power. So let's go ahead and see if we can simplify these expressions underneath. Okay, first I have 6y squared raised to the third power. So remember, that's the same as 6y squared times 6y squared times 6y squared. Notice that I have 3 6's. Ooh, I forgot my 6 there. I have 3 6's that I'm multiplying together. So I could write that as 6 to the third power. And if you remember, there's really a 1 right there. 1 times 3 is 3. Times y to the 2 4 sixth power. All right, 2 times 3 gives me 6. Now we're going to evaluate 6 to the third power. 6 times 6 is 36, times another 6 is 216. So this expression becomes 216y to the sixth power. Next, I have -3n to the fourth. That whole expression is being squared. All right, so remember there's a 1 right here with my -3. 1 times 2 is 2. So this is going to be -3 squared times n to the 4 times 2 is 8th power. All right, n to the 4th squared is n to the 8th. Now if we square -3, that gives us +9. So the expression is going to be 9n to the 8th power. Finally, we have -10a to the 5th. That whole expression is being raised to the third power. So again, I'm going to have my number -10. That's going to get raised to the third power. Again, there's a 1 there. 1 times 3 is 3. And then a is going to be raised to the 15th power because 5 times 3 is 15. Now let's evaluate -10 to the third power. That's going to be -1000. And then times a to the 5th power. For our next exponent property, we're going to be dividing numbers that have the same base. This time our expression says 3 to the 5th power divided by 3 to the 2nd power. How can you rewrite this as 3 with a single exponent? All right, well, first we're going to rewrite the expression in expanded form. So we have 3 to the 5th power over 3 to the 2nd power. 3 to the 5th power is 3 times 3 times 3 times 3 times 3. And that's all going to be over 3 to the 2nd power, which is 3 times 3. It's important to remember that any number divided by itself is equal to 1. All right, simplify as many common factors of 3 from the numerator and denominator as you can. All right, so I have a 3 in the numerator and a 3 in the denominator. 3 divided by 3 makes 1. I have another 3 in the numerator and denominator. 3 divided by 3 makes 1. Okay. Finally, rewrite the expression as using a single exponent. In this case, I can't factor out any more 3's because I don't have any more 3's in the denominator. So now, if I look at my numerator, I still have 3 3's, which means it's equal to 3 to the third power. 3 to the 5th power divided by 3 to the 2nd power equals 3 to the third power. What do you notice? All right, well, hopefully you noticed again that we're going to keep the base the same. That's our 3. But to get the exponent this time, 5 minus 2 makes 3. You need to subtract the exponents. And that's exactly what property number 3 tells us in the box underneath. Okay, so let's investigate property number 3. We're told that when you subtract expressions with the same base, you keep the base and you subtract the exponents. X to the a power divided by x to the b power is equal to x to the a minus b power. Okay, so let's practice simplifying expressions. And again, we're going to rewrite these where we're going to be using a single exponent. 9 to the 7th divided by 9 to the 3rd, the bases are the same. Keep that base, subtract the exponent. 7 minus 3 is 4. 9 to the 4th. 3 to the 2nd divided by 3 to the 8th. The bases are the same. Keep that base. And now subtract the exponents. 2 minus 8 is negative 6. We have a negative exponent. We'll talk more about that in a moment. N to the 7th power divided by n to the 4th power. N is the same base. Subtract the exponents. 7 minus 4 is 3. So we get n to the 3rd power. And finally, x to the 4th divided by x to the 5th. Keep x as your base. 4 minus 5 is negative 1, another negative exponent. Okay? Underneath, it says that, notice that in 2 of the examples above, the exponent was negative, right here in letter B and here in letter D. A positive exponent will tell us to repeatedly multiply by the base, and a negative exponent will tell us to divide. All right, so let's take a look now at what it means to have a negative exponent. Let's investigate negative exponents. In our last examples, we had a couple of exponents where they turned out to be negative numbers. Consider the expression 3 to the 3rd power divided by 3 to the 5th power. How can we rewrite this as 3 with a single positive exponent? All right, well, first rewrite the expression in expanded form. So this is similar to what we were doing before. 3 to the 3rd divided by 3 to the 5th is the same as, in the numerator, 3 to the 3rd is 3 times 3 times 3. And in the denominator, 3 to the 5th is 3 times 3 times 3 times 3 times 3. Well, we know from using our last property that all I would have to do is keep the base and subtract the exponents. 3 minus 5 is negative 2. All right, but I want to write this where the exponent is positive. So let's take a look at our expanded forms, okay? We're now going to simplify as many common factors of 3 from the numerator and denominator as we can. We have 3 3's in the numerator, 5 3's in the denominator. That means I would be able to factor 3 3's from each. 3 divided by 3 is 1. 3 divided by 3 is 1. 3 divided by 3 is 1. Notice that you have simplified all 3's from the numerator. This means that the numerator is equal to 1. Remember that all these became 1's. 1 times 1 times 1 is 1. You still have 3's in the denominator, so write the denominator as 3 with a single positive exponent. Okay, so again, my numerator is 1, but in the denominator, I still have 3 times 3, which is the same as 3 to the 2nd power. Okay, so this 3 to the 3rd divided by 3 to the 5th is the same as 3 to the negative 2nd power, but it's also the same as 1 over 3 to the 2nd power. 3 to the negative 2nd power equals 1 over 3 to the 2nd power. And there I have 3 with a single positive exponent. Now, with the exception of scientific notation, which is the lesson that we're going to be learning next, negative exponents should never be left in your answer. We take the reciprocal so that the exponent will always be positive. So now that we have a better understanding of negative exponents, we'll just talk about property number 4, which tells us that if an exponent is negative, take the reciprocal so that the exponent will be positive. X to the negative a power is equal to 1 over x to the positive a power. Okay, so remember, we don't want to have any negative exponents in our answer. We'll always take the reciprocal so that the exponent will be positive. So let's rewrite each expression using a single positive exponent, and then we'll evaluate any numerical bases. Here, in letter A, we have 4 to the negative 3rd power. Since the exponent is negative, I'm going to use the reciprocal to make my exponent positive. This is going to become 1 over 4 to the positive third power. Now this is a numerical base. I'm going to evaluate it. In the numerator, I'm still going to have 1. In the denominator, 4 to the third power is equal to 64. 4 times 4 is 16, times another 4 is 64. So this expression is equal to 1 over 64. In letter B, we have 10 to the negative fifth power. Negative exponent means I'm going to use the reciprocal, 1 over 10 to the fifth power. And now when I evaluate that, again, my numerator is 1. 10 to the fifth power is equal to 100,000, a 1 with 5 zeros after it. So this is equal to 1/1000th. H to the negative 13th power. Negative exponent, use the reciprocal. 1 over h to the 13th power. And I can't evaluate this because I don't know what the value of h is. Finally, in letter D, 10 squared raised to the negative third power. Now, the first thing that I realize here is that I'm multiplying a power to a power. So I'm going to go ahead and use the power to a power rule. I have 10 squared to the negative third. I'm going to keep the base of 10. And then I'm going to multiply the exponents together. 2 times negative 3 is negative 6. So this expression is equal to 10 to the negative 6th power. Now I have a negative exponent, and I'm going to use the reciprocal, which means it's going to be equal to 1 over 10 to the 6th power. And now when I evaluate this, my numerator is still going to be 1. But in the denominator, I'm going to have 10 to the 6th power, which comes out to be 1 million. So our final simplified expression is going to be 1/1 millionth.